Alright, we're doing section 11.2 today. The topic's called combinations, but it's connected really to what we did last day. So, to try to show you what's going on, I want you to think back to what we did last day, okay? I've got a situation here. I've got a group of 5 students, and 3 are to be elected to become part of the executive of student government, okay? So your student council at the school. There's no title, so it's not president, vice president, treasurer, it's just they get to be on the executive. So in this case, the order of choosing the people does not really matter, right? Doesn't matter if you're chosen first or third. Hey, you're chosen. So the question I have for you is, how many ways can the positions be filled from this group? So out of 5, I want to choose 3 individuals. Well, you know how last day when we talked about permutation of repeated objects? Well, I can kind of look at it that way as well. Because out of the 5 individuals, I'm going to have 3 winners and 2 losers. Okay? And really, the order of it doesn't really matter. So, from last day, what we did was we used that lovely formula, n factorial over a factorial, b factorial, c factorial, so on and so forth. Remember, a is the number of alike objects of one kind, b is the same as that, and so on and so on. So in this case, we would have had 5 factorial over 3 factorial times 2 factorial. Okay? And so we got 5 times 4 times 3 times 2 times 1. Here we have 3 times 2 times 1 and 2 times 1. Those disappear. 3 and 3 disappear. So we're left with, I believe, just 10. Okay? So we did a question like this last day, right? With that idea. Well, I want to extend that idea because when the order does not matter, we have a special name for this. We call it a combination. And then remember how we had symbols for the permutation? We have a symbol for this too. It says in the above example, this is a combination of 5 items taken 3 at a time. And the symbol, okay, we have here is now not 5p3 but 5c3. Okay? So this whole thing here is equal to 5c3. Now, let's see if we can generalize this, okay? Because in these cases, there's always only 2 possibilities. You only have a winner and a loser, okay? So we only have A and B. There's no C, D, E, F, G's, and all that kind of stuff. So in general, the number of combinations of n items, so that's like the 5, taken r at a time, is given by this symbol NCR. And there's a formula for this symbol, NCR. Now, let's see if you can come up with the formula. So, by looking at our previous example here, the 5 factorial, 3 factorial, okay, how can we use those numbers 5 and 3 and replace the 5 with the n and the 3 with the r? Let's see what we get. Well, we have 5 on the top, so that's just our n factorial. So we have n factorial. Now we have a 3 factorial on the bottom, which is our r things taken at a time, so r factorial. Well, the question now is, what's this part? What's this 2 factorial? How do we get that? By using the numbers 5 and 3. And if you said, hey, 2 is just 5 minus 3, you're correct. So in general terms of n and r, this next factorial must be n minus r. Okay? Right? So think of it as this. These are the winners, right? There are winners, and the rest are losers. Okay? And the number of winners plus the number of losers must equal to the number of people n. So, here's the big formula for today for the combination. NCR is equal to n factorial all over r factorial times n minus r factorial. Okay? Got that? And you're well on your way. So let's look at example number 1. From a group of 9 math teachers, there are 4 that are going to be selected to teach summer school. So the question is, in how many ways can this be done? Well, if you think about what's going on, I've got n equals to 9, and I want how many winners? I guess there are 4 winners. So if you use that idea of NCR, because order doesn't matter here, equaling n factorial over r factorial n minus r factorial. That means we have 9 choosing 4. So that's 9 factorial over 4 factorial times 9 minus 4 factorial, which is just 5 factorial, right? 4 winners means there's 5 losers. We're going to calculate this by hand. Four times 3 times 2 times 1, 5 times 4 times 3 times 2 times 1. Well, that's great. Those disappear. 3 times 2 is 6. Those disappear. The 4 and 8 simplify, so that's 18 times 7. How about 126 different ways? Okay. Alright, so if you feel good about this, turn the page. Let's try another example here. Okay. Alright, now we got 10 girls and 15 boys that tried out for the school's badminton team. And the question is, in how many ways can the official team be selected if the official team has 8 members? Now notice here, 8 members. Didn't talk about male, female, just talked about general members. So maybe they could be all boys, they could be all girls, or a mix of each. So in this case, we're just talking about members. I'm going to ask you how many members are going to be, how many people are actually on this team? Yeah, 10 girls and 15 boys. So how many members is that? I guess there are 25. So there's 25 different people to choose from. How many do I want? I want 8. Does the order matter? So there you go. Your answer here is just 25, C, 8. Now, we can calculate this by hand, but for those of you who have a graphing calculator, bring it out because the graphing calculator has a feature on here that you can use. Just take 25. Now press math. Go to the PRB, choose number 3, and then choose number 8. Voila. That's a lot of ways. 1,081,575 ways. 1,081,575 ways. Lots. What happens if I split this up? 4 girls and 4 guys on the team. Well, now you're saying I have to choose some girls, and then I have to choose some guys. So I think we have to split this up. We've got to talk about the girls, right? Then we got to talk about the guys. Now for the girls, how many girls do we have? Yeah, there's only 10 girls. So we have to choose from 10. And we want 4 of them. So R is 4. I guess that's 10, choose 4. Well, how about the guys? There's 15, right? And then we want to find 4 of them. So that's 15, choose 4. Now, think about what these numbers are. I guess we can calculate them using our calculator. So I'll just go 10, choose 4. That's 210. Okay, that's cool. And then 15, choose 4. We got 1,365. Okay, so now what? Think back to what we did in section 11.1. Think about this, like, here's me, captain, and I'm choosing 4 girls, right? So I've chosen the 4 girls, I draw the branches, and in this case there are 210 branches, or 210 ways. Well, what do we do afterwards? Then we have to choose a guy, okay? So then from each of the little branches we branch out again, right? Branch out again, branch out again, branch out again. And in this case there are 1,365 ways to choose a guy. Does this look anything like the fundamental counting principle, where we had to multiply them together? So your final answer is really just taking the number of ways to choose 4 girls, and you're going to multiply that by the number of ways to choose 4 guys. And that would be your total. 210 times 1,365. Done. 286,650. 286,650, and that's the total number of ways. So just do them separately, then multiply them because of the fundamental counting principle, and there you have it. Okay? Alright, let's try part C. Same kind of question, okay? At most now I can have 3 girls on the 8-member team. What does the word at most mean? Give me at most 3 girls. I guess that means you can have 3 girls. What else could you have? 2 girls, 1 girl, or no girls. So really what I'm saying is let's take a look at the number of possible ways to have no girls. Or you have 1 girl, which means then you have how many boys? 7 boys, right? Yeah. So it's implied. 2 girls, which means there are 6 boys then on the team. Or, like you said, 3 girls, because it's at most 3, which means there's 5 boys on the team. Okay. So, in this case, what are we going to do? Well, no girls is also equivalent to saying all boys, so 8 boys. So, like from above, I could say, well, in this case, I've got n equals to 10 for the girls. I want to choose none. In this case, I have 15 boys, and I want to choose all 15 to be on the team. Or not all 15. 8 of the 15 have to be on the team. And so here's what we have. Okay. Now we can do the same thing for each other situation. N equals to 10, by the way, in all these cases for the girls. But notice how R changes. And for the boys, it's always going to be 15 boys we're choosing from. But notice how they change as well. Okay, so let's write out the combinations. Okay, here we go. This is then 10 choose 0. And just like the previous one, we're going to multiply that by 15 choose 8. Here we have 10 choose 1 multiplied by 15 choose 7. 10 choose 2 multiplied by 15 choose 6. 10 choose 3 multiplied by 15 choose 5. Okay. You can do this on the calculator, okay, and get all the numbers. I've done it already, so I'm just going to write them out for you. Save us some time. I believe this is 64350. I believe this is 64350. This one is 225225. You can double check this for me. 360360. Okay. Now, we've got these 4 different situations. Now, what do we do? It says at most 3 girls. And we went back to the beginning step. It says at most 3 girls, meaning no girls, or 1 girl, or 2 girls, or 3 girls. So I want all these different possibilities because they all work. So if I want them all, I'm going to have to add up all these different ways. And if you add them up, you'll get a final answer of 656370. A whole bunch of ways. Okay? That many combinations. Okay? So notice we multiply when we had the fundamental counting principle. We have this and that. But when we have the word or, we're trying to include everything, so we add. Okay? Alright, I'm going to ask you to try example number 3 now. Okay? I'm going to maybe show you the first little bit, but the rest is on your own. Here it says the bag contains 5 lollipops and 8 candy canes. How many ways can you draw groups of 5 candies if at least 3 must be lollipops? Here's the key word. If at least 3 must be lollipops. At least 3, meaning the minimum number is 3. So 3 lollipops. Or what else can you have? 4 lollipops. Or 5 lollipops. Or 6 lollipops. Oh, wait a minute. The bag only contains 5, so don't worry. Stop at 5. Okay, so remember, 3 lollipops also means then, I guess you're choosing 2 candy canes, because you're choosing 5 in total. 1 candy cane, no candy canes. Okay, I think I've given you enough now. I'd like you to try to complete the rest. I'll be quiet. You stop the tape, you do it, then come back and double check the answers. Go. Happy? Got the answer? Good. Let's move on. Many of you play cards. If you don't, well, get used to them because we use them quite a bit in these combinations, counting type questions. So here's another example here. I'm going to tell you that we've got a standard well-shuffled deck of 52 cards. Okay, and in a deck of cards there are 4 suits. Those are the kind of symbols on it. So you've got the spades, the hearts, the diamonds, the clubs, of 13 cards each, because then you have the rank. So like you have the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Okay, so that's why there's 13 different ranks. So that's why it's 13 cards each. Question and a half for you is, how many different 5-card hands can be formed? Well, I didn't care about what type of cards, so now we're talking in general terms. So how many cards do I have to choose from? And how many do I want? You should always ask yourself that. In this case, I got 52 cards, 5 that I want. Does the order matter? It doesn't. So we have here 52, choose 5. Numbers this big, forget it. Doing it on the calculator. Turn on the calculator first, right? 52, math, from 3, 5. Bing, bing, bing. 2, 5, 9, 8, 9, 6, 0. 2, 5, 9, 8, 9, 6, 0 ways. Cool. What if I change this now? Be a little bit more selective. I said, how many ways can you select 5 cards if 2 of them are spades? So now I'm saying, okay, I'm still selecting 5 cards, but I want spades and non-spades. Out of the 5, I want 2. Was it? No. Yeah, 2 spades, right? So, how many spades are in the deck? Yeah, there are 13 spades, right? 13 spades, and I want 2 of them. How many non-spades are in the deck? Well, 52 cards, subtract 13 spades. That must be 39. So 39 non-spades. And how many of those do I want? I want 3. So what will we have? How about 13 choose 2? And then 39 choose 3. And then of course we want to just multiply them together. Fundamental counting principle. And let's see what we get. 13 choose 2. 13 times 6. That's 78, I think. You can double check my answer. 39 choose 3. Yeah, I can't do that in my head. 39 choose 3. 9139. Okay, 9139. Gonna multiply that by 78. Let's see what we have. Whoa, 712,842. 712,842 ways. 712,842 ways. Yeah. Okay. Well, you can do part C now. I think part C is very similar to part B. So, how many ways can you select 5 cards if 3 of them are clubs and then 2 of them are hearts? So, you can think about this. So, out of the clubs, how many clubs are there again? Yeah. 13, right? Choose 2. 3, sorry, choose 3. Out of the hearts, 13, choosing 2. Okay. Well, I think that's it. Write it in the combination form. 13, choose 3, times 13, choose 2. Go ahead and calculate. 13, choose 3. 286. 78. So we had that from above. 22308 ways. Okay. How about the next one? 5 cards if 3 of them are face cards. Well, which ones are the face cards? Those are the pictures on it. That's your jack. That's your queen. And I believe your king. So there's 4 of each, right? So total number here would be 12. So really what I'm saying is you got your face cards, you got 12 of them, and you want to choose 3. And then I guess the rest that you choose are non-face. So how many non-face cards are there? 52 take away 12. 40. And I guess I want 2 of those. So translating them into combinations, 12C3, 40C2. Whoa, what did I just do there? And just like the previous ones, we multiply them together. Okay? You go ahead and calculate this on your own. I will just wait for you. Ding. Time's up. I hope you got this too. Yay! Alright, one more from this example. How many ways can you select 5 cards that consist of at least 1 diamond? Okay. Oh boy. At least 1 diamond. That means there's 1 diamond, or 2 diamonds, or 3 diamonds, or 4, or 5. Whew. I guess we just have to do all of them then. That would be, out of 13 diamond cards, I'm going to choose 1. Out of all the remaining cards, the non-diamonds, which are 39 of them, I want to choose 4 of them. In this case, I got 13, choose 2. Because out of the 13, I want to choose 2 diamonds. Out of all the non-diamonds, 39, I need now 3. See the pattern? You finish off the rest. And then OR means you have to add them up. And you're thinking, oh my goodness, that's a lot of punching the calculator. Yes, it is. So, you can do it that way, which I think many of you will, and it'll take a while. Some of you might be thinking, wow, is there a faster way of doing this? So, while I write the answer to this, I'll let you think about that, and if you think of a faster way, tell me. Or tell yourself, okay? Think of a faster way yet? Because this is taking a long time. And I'm just speeding up because I did this earlier. But if you're doing this in tests, you'd be spending like 15 minutes on it. Well, not maybe not 15, but a lot of time. What can we do? Too many calculations. Okay. Anybody have an idea? Text me right now. Oh, wait a minute. You don't have my text, so you can't. Well, if you do, shout it at the computer screen. The computer screen will give you 1 beep if you're correct, and 2 beeps if you're wrong. Go. Did the computer screen give you beeps? Oh, okay. Guess your computer doesn't work. Alright, how can we actually do this in a better way? You can. Sometimes it's nice to talk about what we call the complement, okay? So it's kind of like if I want 3 things from a group of 5, it's the same thing as saying I don't want 2 things from a group of 5, right? So we're going to use this idea of complement. What do you think is the complement of at least 1 diamond? Well, the opposite of or complement of at least 1 is taking none. Right? It's like me saying the opposite here is no. None. None. No diamonds. So really what I can be doing here is taking a look at the number of possible ways just to, in general, select 5 cards, and then from there subtract the number of ways to get no diamonds. And that should give me the same answer of at least 1 diamond. So I'll say now at least 1 diamond is equal to then taking all of them, right? So at least 1 diamond is just selecting 5 cards, okay, minus the idea of selecting no diamonds. Well, selecting 5 cards, what's that? That's, I think, 52 choose 5. And then no diamonds, what's that? Well, that's, I guess, out of the 13 diamonds, I want none of them. But out of the remaining 39, I want 5 of them. And go ahead and calculate this on your calculator. 2598960. That's from part A. And then this is, I think, 575757. So if we do this subtraction, we get the same answer. Okay? Same. But with so much less work. Whew! Alright, your brain might be fried by then, but I got 3 more to do. So if you need a break, take a break, and then come back. Otherwise, let's power through these last few examples. Okay? Here we go. You need to also solve equations. So yeah, just like permutations, we need to know how to solve them. So recall NCR equals to n factorial r factorial n minus r factorial. So first one, I guess I'll rewrite NC2. N factorial n minus 2 factorial. Oops. Oh, it doesn't matter. Order doesn't matter. 2 factorial equals to 10. 2 factorial is just 2, so I'm going to simplify this to this. And I'm going to put the 2 on the other side, so 10 times 2 is 20. We know this can be simplified. You should know how to do that from last time. That's n minus 1, n minus 2 factorial. So notice the n minus 2 factorials cancel out. So you're just left with n minus 1 equals 20. N squared minus n equals 20. It's going to move up here. Do some nice moving everything to one side. Oh yeah, time to factor again. That's my factoring. I hope that matches up with yours. Solve, we get n equals to 5. Here you get n equals to negative 4. And remember how n has to be a natural number, so goodbye 4. And therefore the only solution is n equals to 5. Alright? Okay, I'm going to ask you to try B on your own. It's very similar to A. So do that, then come back when you're done, and then I'll show you C. R factorial n minus r factorial. I think that simplifies to 2 factorial. Well, that's 30, so that's n plus 1 factorial. N minus 1 factorial equals to 30. Now it's n plus 1 times n. That's what's left over. I'm skipping a few steps because I'm hoping that you are doing this yourself. I think in this case n also equals to 5. Okay. Alright, last one's a little bit different because I got 3 in front. So let's ignore the 3 for now and just do the same things, okay? So 3. And then if n factorial, 3 factorial, n minus 3 factorial. Over here on this side you have n plus 1 factorial. This is n, 4 factorial. N plus 1 minus 4. So that's just n minus 3 factorial. Okay? Kind of combine a step there. Hey, look. N minus 3 factorial there. N minus 3 factorial there. Goodbye. Alright, now we have 3 times n factorial. 3 factorial is just 3 times 2 times 1. Here we have n plus 1 factorial, and we have here 4 times 3 times 2 times 1. I like this. 3 times 2 times 1, 3 times 2 times 1, they're gone. And I can move the 4 now to the other side. So how about 12 times n factorial equals to n plus 1 factorial. This looks much better now. I'm going to now isolate the 12 and then bring the n factorial over here. N plus 1 factorial divided by n factorial. What's that going to be? You can try to simplify that. That's just n plus 1. And so therefore n equals to 11. And by the way, with all these algebraic equations, you can always double check this, plug n back in, and just kind of say, well, 3 times 11c3, is that equal to 12c4? And I'll leave that as an exercise for you to check. And if you check and it's good, then you're good. And so are we. See you next time.